I see that the population's a little thin today. I wonder if it has anything to do with the homework. But yes, there is a homework due today, midnight, and as always, you get an extra day if you are willing to give up 10%. And now might be a little late to start, but I'm guessing you guys are here, you look happy, so probably you're done. Any questions about the homework? Yes.
I get confused between counting literals and counting assignments. I think that's my problem. So why when you're counting Boolean functions, you're exponential and then because you're counting the outputs to be either 0 right? But when you're counting conjunctions,
Right.
you're not exponential in n. Is that because we're not counting whether?
No, conjunctions are also exponential in n.
But then
Conjunction,
how is it tag learnable?
log of that is not exponential.
Well,
So
okay,
now-
so counting Boolean functions 2 to the 2 to the n.
Yes, and log of that is exponential.
And log of that is exponential.
Yes.
When you're counting conjunctions, when I first thought of it would be 2 to the 3 to the n because you're counting the output to be
No,
either
no,
0
so
or 1.
actually no. Well, first of all, here's a simple proof that it can't be 2 to the 3 to the n because every conjunction is a Boolean function. So the number of conjunctions has to be less than the number of Boolean, less than or equal to.
Right.
So it can't be more than 2 to the n.
Okay.
Okay, so
That makes sense.
So that's one side of the argument. When we are counting Boolean functions, we are actually counting number of possible functions by looking at the outcomes, right? When we are counting conjunctions, we could have done that, but actually there's a much easier counting mechanism which says we'll just construct functions and count how many they are.
Okay, so the output is dependent on whether we include an input or not.
The output changes.
The output changes.
Yes.
Okay.
So we are implicitly counting the number of possible outcomes by explicitly constructing functions. Remember that a function can be defined either as a map from some input, basically this map that covers every possible input. That's what we did for all Boolean functions. Or it can be defined as in an algebraic fashion. They are equivalent, right?
As what?
In an algebraic fashion.
Uh-huh.
So I can define a function f of x equals x. This is my shorthand for saying all pairs of x comma x. An infinite set.
I didn't hear it.
Okay, so I can either define a function algebraically,
Uh-huh.
as in let's take booleans for example. F of x is x and f of x1 x2 is x1 or x2. This corresponds to one possible assignment to any values of x comma x1 x2, right? So this is an algebraic construction of the function. I can either write the function down in this algebraic fashion, or I can write it down by listing the outcome for every possible input.
Okay.
For when we are counting Boolean functions, we did the latter. We listed all possible outputs.
That was the easiest way.
That was the easiest way to do that. When we are counting conjunctions, it turns out it's easier to explicitly just construct the algebraic version of the function.
Right.
And it turns out that's the best way to do it for conjunctions, monotone conjunctions, disjunctions, three K conjunctions, and all those things.
Okay. I understand that.
Yeah.
Okay. And then, sorry. Someone else had a question.
Mine's more logistical. I was just gonna ask, you got those updates on the
Yeah, yeah.
projects? Do you get feedback?
Yes,
Okay.
I haven't started reading them yet. I'll probably start tomorrow, and my hope is I get back to you by this weekend, by the end of the weekend. Yes, and if you feel that you need feedback immediately, either send me a message through Canvas or email. I know that there is one email that I have managed to lose. I can't remember who it is. So if you sent me an email in the last month and I did not respond, please send it again. Were there other questions? Yes.
When we were talking about the number of samples for something to be tag learnable,
Uh-huh.
we used an example that only had 2 possible labels.
Yes.
So what happens if you have more labels?
You can define the idea of, say, for example, shattering in a similar way. The math looks slightly different, but not much. The general ideas carry over. I can define VC dimensions for multi-class classifiers. I can define, I can count the number of multi-class classifiers. How many possible functions are there? The counting argument changes slightly because you're no longer doing, say, the number of outcomes is no longer 2, but more than that. But the general flavor of the results remains the same. And in fact, if you have to use this, you can just use log of size of h inside the, it boils down to log size of h eventually.
So if your labels increase your hypothesis space, then the Occam's razor formula will still like capture that increase of labels?
There might be differences in the actual constants, and a little bit of maybe an epsilon or 2 around here and there, but the order of magnitude will be the same, of sample complexity.
What's the intuition that we should have for that? Like, to me it's a little bit confusing to think of functions with like binary inputs giving multiple different
So in fact I suspect the question in your homework has something like that. You have binary, so let's say one example is, say I want to build a sentiment detector, and there's a tweet and I need to decide whether it's a positive or a negative or neutral in sentiment. And as features, I'll use indicator features for words in the tweet. So the inputs are binary, the outputs are, in this case, can take 3 values. So what do you mean by what's the intuition?
I know, so for me it's a little bit confusing to think about how you could find a single function that takes binary inputs and gives more than binary outputs. You know, I don't know why that's...
Oh, but think about it this way. How many binary inputs are there? Let's say we have 10 features. The number of possible binary inputs is 2 power 10. There are 2 power 10 unique Boolean strings, right? What you're doing is creating a map from this set that's 2 power 10 to another set that, say, has 3 elements. You can create a map, right? Nothing stops you. You can say that all zeros maps to the first element, all ones maps to the first element, and so on. You always do. So that's a function. So don't think of the binary, what do you call it, the individual features being binary. Think of the entire instance, the entire feature vector. There are clearly more than 2 of them. So you can map that to multiple objects.
Okay.
Would you operate on many-to-one mapping?
We do not generally assume that. Oh wait, many to one, yes, not one to many. Yes, many to one, yeah, totally fine. In fact, all of these are many to one, right? When we do binary classification, it has to be many to one. When the number of features goes beyond 1. If you have 2 features, you have 4 inputs and 2 outputs, so it has to be a many to one map. Yes. You had another question.
No, I'll come later.
Okay. Probably other people have the same question, so you can ask if you want.
No, it escaped me.
Okay. Other questions? Yes.
I have a question about the one decision list and how to prove it being acceptable. So I think maybe you can give me some hints.
Yes. That's actually the hint is actually the construction. So to prove that a one decision list is linearly separable, there is a constructive proof. You can prove that by actually producing a weight vector and a bias that always agrees with it. And the way you should think about it is, let's say you have a one decision list. By definition, there's an ordering of the features, right? The first feature is clearly more important than the rest. Second feature is more important than all features except the first one. And so on. So as you go down the list, features become less important. Meaning, if I make a decision here, I don't even read the other features. So now you want your weight vector to capture this relative ordering. I'm not going to give you a stronger hint than that, because if I say more, I'll be giving you the answer.
Thank you.
Other questions? So, yes, a few people just came in. Yes, there's a reminder, there's a homework due today. And if there are no other questions, I'm going to move on to the topic of today's lecture, which is support vector machines. So we are going to by the way, this is a picture from the CMU machine learning protest where people had cards saying support vector machines and other things. And this is what passes for a joke in the machine learning world. So, in any case, where are we? We've looked at different learning algorithms. We've looked at decision trees, nearest neighbors, perceptron, Winnow. Last week we saw AdaBoost. And many of these are linear classifiers. In fact, the last three, including AdaBoost, is a linear classifier. From the perspective of general ideas in machine learning, we've seen a lot of ideas that actually apply to all these things. We have looked at the idea of overfitting, and this is something that we have to watch out for, irrespective of what classifier you're training. We've looked at the curse of dimensionality. We looked at this question of what is learning, and we try to answer that by saying learning is when this classifier stops making mistakes, and that gives us the mistake bound model, and under that model we analyze perceptron and Winnow. We defined learning in a different way. We said learning is this situation where with high probability this algorithm, I don't know which algorithm, some algorithm produces a classifier that has low error. And this is the idea behind, intuition behind pack learning. And we looked at, looking at pack learning gives us this new definition, new idea of complexity. In addition to computational complexity, there's this thing called sample complexity. You want to be able to learn you're asking, when you are thinking about sample complexity, you're really thinking, is there enough information in my training set to be able, that any learning algorithm can possibly learn? And along the same lines, we also looked at the fact that the size of the hypothesis class is important. And for infinite dimensional hypothesis or infinite hypothesis classes, we defined this idea called VC dimension, which acts as a surrogate for the size. The VC dimension measures the complexity of a classifier of a class of functions by saying what's the largest number of what's the size of the largest set of points that it can shadow, that it can possibly label. And VC dimension and or the size of the hypothesis class is a natural way of us measuring how difficult is this function, or is this function class expressive enough. And the other thing we looked at is this relationship between training and generalization errors. When we talked about agnostic learning, we can measure training error, we can try to minimize training error, but what we really want is low generalization error, and we are asking, if I have low training error, can I say anything about the error in the future? So in the next few lectures, we are going to see how, we have already seen an example of how learning theory actually directly led to the development of a learning algorithm in the form of AdaBoost. Today and maybe in the next one or two lectures, we'll be looking at how learning theory, all these ideas that we looked at, gave us a way to reason about learning and gives a framework for basically generating learning algorithms in the form of minimizing loss. So we'll be talking about something called loss, and we'll define learning in the following way. We'll write down something called loss. Loss, as the word suggests, is something that we don't like. And we'll define loss of a classifier, and we'll define learning to be find the classifier that has the lowest loss. But to get there, we are going to kind of go in a slightly roundabout way. And I'll start off with support vector machines and point out that it's an instance of this loss minimization, which it turns out encompasses many learning algorithms, including SVMs, logistic regression, boosting, perceptron, and these days it's become the standard way in which if you write down a new set of new hypothesis space, a new set of classifiers, like say 18-layer neural networks, you don't try hard to think about, oh, okay, now I have a neural network, I need to think about how to define a learning algorithm. You just define loss, and you reduce your problem to an optimization problem. This is also called the risk minimization principle or the empirical risk minimization principle. And everything that I said in the last, say, minute is a preview of maybe the next 2.5 weeks. Just to remind you of the big picture, we've been looking at linear models a lot. Consistently, we've been looking at multiple learning algorithms for linear models. And the question that we've been also worried about very often is, what is learning? How good is a learning algorithm? And when we tried to answer this question using the idea of online learning, this combined with the idea of learning linear models gives us algorithms like perceptron and WinOp. The last few weeks, we looked at learning theory, PAC, and agnostic learning, and support vector machines are a class of algorithms that come into existence because PAC learning met linear models. We'll be looking at at least one more way of asking the question, what is a good learning algorithm? Questions about the big picture with respect to where we are. Yes.
So I kind of made this connection when I was working on the homework. It's just kind of a question or comment. But, so with PAC learning, what we're saying is, some kind of problem is PAC learnable if two things. There's this a learning algorithm, and that learning algorithm. Let's see, how do I say it? I guess what I'm trying to say is it seems like when we were talking in lecture, we focused on like the number of samples that are required, but we also need to have a learning algorithm that produces a consistent hypothesis
or minimizes the training error.
Yeah. So you have to show that to show something's PAC learnable, you have to show that you have a consistent learner and the
So in fact, we did see this point in the class as well, which was the distinction I made between PAC learnability and efficient PAC learnability. PAC learnability says there is enough information in the sample space, in the training set, small enough training set that some learning algorithm, there may be a learning algorithm that can learn. Doesn't say anything about the computational complexity of learning. Efficient PAC learnability says, yeah, sure, there is enough information, but can you show me an algorithm that actually runs in a reasonable amount of time? Without that, and in fact, there are a few concept classes which are PAC learnable but not efficiently PAC learnable.
So yeah, with PAC learning, we just need to have a learning algorithm that chooses any consistent hypothesis, right?
Yes.
It can be a really dumb, like it could be the halving algorithm.
Yes.
Or,
yes.
Okay.
And I don't want to stress the point of consistency too much, because any real world data, you're not going to get a consistent thing. So if you want the most general version of the story, think agnostic.
Right. So we want a learning algorithm that minimizes the training.
Exactly.
Okay.
Exactly. Good question. Other questions? Okay, so let's look at support vector machines. The slide says this lecture, but this is going to be the next 2 or 3. And the entry point into support vector machines is to think about learning as is to frame learning as a margin maximization problem, and that directly leads us to the idea of support vector machines, where we write down learning as an optimization problem. Once we write down the problem of learning as numerical optimization, in theory, problem solved, because numerical optimization has been studied for decades. We can just give it to people in the math department and move away. It turns out by thinking about optimization, we can come up with learning algorithms that are actually pretty simple and only so big that they'll fit in this slide. And I'll show you an example of an SVM optimizer that you'll actually be implementing in your next homework, which does the trick, and it's one of the state-of-the-art learning algorithms. After that, we'll talk about why this thing is called support vector machines, and talk about this idea called, one of the coolest ideas in machine learning, it's called kernels. And it turns out it comes from math, but kernels are a way of thinking about nonlinear classifiers without actually worrying too much about giving up on your linear, all these linear learning algorithms. And I'll wind up this section by generalizing this idea of learning by risk or loss minimization, just to point out there are some very close connections between SVMs and perceptron and such things. And we'll see that probably in a week and a half. So let's start with this idea of maximizing the margin. The story starts again with VC dimensions. We've seen this before, or some version of this, where we talked about agnostic learning with the infinite hypothesis class case, and what we saw was the true error, that's error sub d of a hypothesis, has to be less than the training error plus a term that basically is a function of the VC dimension. And what we concluded is it's good to minimize training error, but it's also good to minimize the VC dimension. And that was our motivation for choosing small hypothesis spaces, or actually function classes that are not very expressive, right? And we saw this in the last lecture actually, and given that you guys have been staring at your homework, this must look very, very familiar. So this is one thing we know. Another thing that we know is that the VC dimension of a linear classifier in d dimensions is d plus 1. So this lets us reason about algorithms like perceptron and Winnow and all those things without actually thinking about the algorithm itself, because it's a linear classifier. And the starting point for the SVM discussion is, really, are all linear classifiers the same? Maybe some linear, given a data set, there might be multiple classifiers that separate the positive and negative examples, but if there are multiple classifiers with the same error, what criterion should you use to pick one over the other? And that's and thinking about this gives us support vector machines. So the way to think about this is to think about the margin. Remember that given a data set, the margin of a classifier of a hyperplane is really just the distance of the closest point to it. So it's something like this. Given this data set, it's how far is the closest point to this separator. And we've seen this before when we talked about the perceptron mistake bound, when we were talking about margins. And I'm going to argue that thinking about this margin and analyzing it carefully gives us a natural criterion for deciding between two classifiers that are equal with respect to the error and yet differ with respect to margin. So to illustrate that, let's say we have the same data set replicated twice, and I have two classifiers, two separators, H1 and H2. From the picture, it's fairly clear that H1 has a smaller margin than H2. And the question to you is, which one would you prefer?
H2.
Why?
It gives us a greater margin, and it's directly in the middle of both sides.
But why is that a good thing?
It's visually pleasing.
It's visually pleasing. Design is the right choice to do machine learning. But think of generalization. Which one of these would generalize better?
H2 will probably generalize better.
And why?
There's more room in the margin, there's more examples come in. There's more room in that margin for it to be on one side or the other.
Yes, there's more room to make mistakes, really. So, suppose a new example comes in, and I've just placed the point in roughly the same place. It's possible that we only have a finite set of examples, right? We have to find our classifier using that finite set of examples, and it's possible that these points might move around in the future when new points come in. If you're picking a classifier that has a larger margin, there is a lower probability of making an error on future examples. And at this point, I'm not making a mathematical argument. I'm just pushing for intuition here. You see this? A new point comes in, it might end up accidentally on the wrong side if you pick a classifier that has a lower margin. It might end up on the wrong side even for H2, but there's more room for it to move. So intuitively, larger margins, better generalization. And the way to formalize this is, suppose you have a collection of classifiers, collection of hyperplanes, all of which separate from the training set. Okay? They are all, using the language from the previous lecture or the one before, they are all consistent with some training data. And suppose you partition them into two sets. One set, it turns out, all the classifiers in set 1 have a margin gamma 1. I'll always use gamma for margin. All the classifiers in set 1 have a margin gamma 1. All the classifiers in set 2 have a margin gamma 2. And suppose gamma 1 is more, then every function in the first set is better by this intuition. Because larger margin, we'll probably make fewer mistakes in the future. Is that intuition okay? So this gives us a way of thinking about subsets of hypothesis spaces. We are now talking about, remember, a hypothesis space is a set of functions, and now we are talking about partitioning this set of functions according to some measure of quality. And we are saying that some of these things are better than others. So H1 here is all classifiers that have a margin mu1. And it's another hypothesis space, right? It's a set of functions. So every partition is also a hypothesis space. And the intuition is a hypothesis space that has a larger margin is better. Yes?
It seems to me that if you had like a large amount of training data, if both you had two different ways of separating the data that were both consistent, that the advantage of the greater margin would be very little in terms of the accuracy. Yes. So is this for like situations where you have very little training data?
It's actually, even then, even if you have a lot of training data and you have two classifiers which are equal in terms of, say, consistency, in terms of training error, doesn't have to be consistent, in terms of training error, let's say. Even then, a classifier that has a higher margin is preferred, because there might be still some cases where it might fall, a new example might fall into that margin, or might fall on the wrong side of the margin.
Yeah, I just felt like it seemed like that would be a very small advantage.
I agree. It's probably going to be a small one as the training size increases.
Okay.
Yes. But this is just an intuitive argument, and I'm going to state a theorem without proof of the way to formalize this is to formalize this by thinking about VC dimensions. Remember that earlier we said VC dimension is just, in all cases, VC dimension is a property of a hypothesis space. You have a set of functions, I can ask what is its VC dimension. H1 is a set of functions, and H2 is another set of functions, right? Both of them are linear classifiers. The only difference is H1 has a margin gamma 1, H2 has a margin gamma 2. And I can ask, what is the VC dimension of a hypothesis space of functions, all of which have a certain margin? H1 is a set of functions. I can ask what's its VC dimension, right? Now, it turned out Vapnik, the same Vapnik from who did the VC dimensions, came up with this theorem. If you have a hypothesis space of linear classifiers, all of whose every element of that set has a margin gamma, then its VC dimension is a function. It's the minimum of either d plus 1 or r square over gamma square plus 1. The details don't matter, but the important thing to note is if gamma is more, VC dimension is lower. And this basically solidifies that intuition. Larger margin gives us a lower VC dimension. And we know that lower VC dimension is a good thing. You have a question?
No.
You look like you do. I'm going to start pointing to people who look confused. So this is a very nice way to reason about this problem. We know from this theorem that if margin gets large, the VC dimension becomes small. And we also know from our understanding of agnostic learning that lower VC dimension gives better generalization. I want better generalization, so I will strive for lower VC dimension. I want lower VC dimension, so I will try to maximize the margin. This gives us a mathematically rigorous criterion for learning linear classifiers. Find a linear classifier that maximizes the margin. Search over the space of all linear classifiers, and now we have two things to worry about. First of all, the linear classifier has to separate the data, right? We still want a classifier. And among all classifiers that separate the data, we are going to pick the one that has the maximum margin. And this theorem will guarantee that we will have the best possible generalization. Questions about this general reasoning, this style of reasoning?
Why large margin leads to lower visibility?
I can give two answers. One is basically this theorem. VC dimension. So, I'm sorry. Oh, if you want a picture, it's basically this picture. Large margin. Okay. So the way to think about it is, there are fewer functions that have larger margins. I can find many more functions that have a smaller margin, because I can move that function around, right? So there are very few functions that have a large margin, and there's going to be only one function that has the maximum margin, or a very small number of functions that has the maximum margin. And we know that if our function space is small, we get better generalization. And that's really roughly the way the proof works as well. Yes?
Would this ever, so going back to that, we have the error on the training set plus that square root of
this one.
Are we going to try to minimize both of those simultaneously?
Yes.
So could you, as a result of this, produce a linear classifier that actually doesn't have zero training error?
Yes, absolutely.
But still minimizes everything?
What we'll get at the end is a knob. On one hand, if we turn the knob all the way to, say, infinity, we will force our classifier to overfit our training set. So it will minimize the first term. If we turn the knob to 0, it will ignore the training set and just find a classifier that has a huge margin. And where you place the knob really depends on how comfortable you are. And probably the right answer, the right way to tune that knob is to use cross-validation. And we'll get there hopefully by the end of next lecture. Yes?
So for an example of the support vector machine, if we had a linear classifier, we have 2 weights and a bias, are we just kind of like looping through?
Okay, good question. So let's talk about the learning strategy. How do you find this classifier? And the one-line summary is you try to find the classifier that minimizes the margin. That maximizes the margin. But that's easier said than done, and there's a whole entire lecture that's going to be talking about how to do it. And the way we'll do it is we'll frame it as an optimization problem, as a numerical optimization problem. And solving that, because you can think of this as optimization, maximize some quantity such that certain properties hold. And we'll see how that works. So to do that, we have to write down, and the general way of writing down optimization problems is you write down an objective, and then either try to write an algorithm to solve the objective, or call the guy who knows to write the algorithm. So let's try to write down the objective first, and I'll talk about how to solve it later. Let's think about the geometry again. So this is a cartoon picture, it's in 2 dimensions. You have a data set that's clearly linearly separable, and let's say there's this line that's defined by W1, W2 and B, that separates this data. The first thing to note is after this separator is found, when a new example comes in, the way we do prediction is to take the dot product of W and X, so W1 X1 plus W2 X2 plus B, and take its sign. We don't care about the magnitude, we don't care about the value of that dot product, we only care about the sign. And we've been doing that all this while. That's how we predict with Perceptron, that's how we predict with Winnow, that's how we predicted with Arabist. So that's the first point. The second thing is just to remind you that the margin is simply the distance of the closest training point to the separator, and obviously you guys know how to calculate distances of points from lines. I believe it shows up in second grade or something. So it's basically the dot product which goes into the sign function there, take the absolute value of that, divided by the norm of W. And that's roughly what's written there. I want to remind you, we only care about the sign and not the magnitude. We only care about the sign of B plus W1 X1 plus W2 X2 and not the actual value. Which means, suppose after learning, instead of this particular line, the learning algorithm had found another line, which is where all these parameters are doubled or multiplied by 100. The predictions are going to be the same. Right? Questions?
Can you just repeat that last part in general, please?
So, because we only care about at prediction time, we only care about the sign of this quantity. Sorry.
Right, and all the weights are equal.
We care about the sign of this quantity. If I multiply everything by 2, the sign remains the same. I can multiply everything by any positive number, the sign remains the same. So if your true concept was this line here, and your learning algorithm found this, you have no reason to complain, because it's going to be exactly right. Even though the actual dot product, the thing that goes inside that quantity there, will be different. And this gives us a little bit of freedom in our choice of W, and we'll exercise this freedom to define the learning algorithm. So to generalize this to arbitrary dimensions, the margin, again, is in all cases, is the distance of the closest point, closest training point from the separating hyperplane. And we've seen this before. The margin can be written as this expression here. You iterate over all training points, xi, yi, and this is simply, this part is simply the distance of that point, xi, from the plane, w dot x plus, actually the absolute value of that is the distance of that plane. If you do not put an absolute value, positive points will have a positive score, negative points will have a negative score.
Sorry, is support vector machine a batch learning or is it an online?
It's batch.
Okay, thank
It's
you.
batch, yes. So, do you see that? Okay, so the distance of this any point from the plane is w dot x is absolute value of w dot b divided by the norm of w. If I drop the absolute value, you get something that has a positive or a negative sign. And it's positive for positive examples, negative for negative examples. And if I multiply that by y, I get back the absolute value because two negatives cancel out. So this is exactly the same as the distance of the point from the line, which is what I have here. And now I iterate over all training examples, xi, yi. I find the minimum of that, and that's my margin. This is simply the mathematical definition of margins. And what we want to do during learning is to maximize this quantity. We want to find the max over gamma no, max overall W and B of min over X comma Y. This is the margin and this is the line. Find W and B such that the distance to the closest point is as large as possible. Because we care about maximizing margin. And just a word about notation, this quantity, and sometimes in the literature you'll see just the numerator alone, y times w dot x plus b is called the functional constant, just the name. Questions? We've seen some variants of this before when we were talking about perceptron.
So are we only going to choose W and B so that we perfectly separate?
For now, yes.
Okay.
For now. Okay? Remember, again, we only care about the magnitude, only care about the sign and not the magnitude. Which means, if I'm able to find a B, W1 and W2 in this picture, such that the distance of the closest point is not B plus blah 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 divided by the norm of W, but 1 over the norm of W. In other words, the closest point has this property. B plus W1x1 plus W2x2 is 1. If I find a W and B such that that holds, then I can frame learning as finding a W such that this quantity is maximized. And just to point out that there's nothing special about positives, you also measure the distance to the negative points. So we have a degree of freedom in that we can scale the entire weight vector by any positive quantity, and let's choose a scale that puts the closest point at a distance of 1 over norm of W. And this means our margin is no longer a function. It doesn't, if I tell you that the closest point is at a distance of 1 over norm W, then I can just try to minimize W to maximize 1 over the norm. And that's really what we are going to do. So to generalize this to arbitrary dimensions, we only care about the sign. So I will set the actual score, the y times W dot x plus b, to be equal to +1 for the closest point. When I say set the score, I will only search over such W's, such that the closest point is at a distance of 1, or actually 1 over norm W. Then, maximizing gamma, which is what we want to do anyway, is the same as maximizing 1 over norm W, which is the same as minimizing the norm of W. This is a somewhat tricky point, and if you've never seen this before, this might seem like there's some cheating going on here. So I want you to stare at it and ask me questions, or ask me questions as you're staring at it. Yes.
Okay, could you repeat one more time why we don't care about the magnitude of W and B?
Think about this picture here. This picture right here. So I have a classifier. Let's say the true classifier is W dot x equals 0. And my learning algorithm gets me something else, 1000 W. The learning algorithm finds a classifier whose weights are 1000-fold multiple.
So you can just scale it.
I can scale it arbitrarily
Okay.
with a positive number. The sign is not going to change. So I'm going to decide to scale it by this quantity here, which is positive, the absolute value.
So you just have to know the sign of W and B so that it's predictable when you're trying
Yes.
to scale it, so that
Yes.
you know what you're doing when you're scaling it.
Yes.
Okay.
So if I'm able to guarantee that the closest point has the property that this quantity here, the numerator, equals 1, if I'm able to guarantee that by appropriately scaling the W, then I can just minimize the norm of W. Questions?
how are we able to guarantee that that will be 1?
Aha, that's our optimization. That gives us our constraint optimization problem. And we'll see that in a minute, in fact right now. What we want is on top. We want to maximize margin. Margin is the value on top. Instead of maximizing margin, I just hopefully sort of convinced you that maximizing the margin is the same as minimizing the norm of the weight vector if the nearest point has a functional margin, which is simply the numerator of that term, has a functional margin of 1. So, yes?
Does it have to be 1, or can we just fix it at like any value? Like why
It can be any value. It can be.
we just choose 1?
We just choose 1 because it's, it makes the math easy.
You're basically saying we're only going to optimize. We're just going to fix. Could you do the opposite and fix your denominator and then try and maximize your numerator?
That's a little bit more painful because the numerator of the margin is a function of the training example. The denominator is not. So the reason we are doing this trick is to get rid of the training data from the objective and move it into a constraint. And that's exactly what this learning problem is. So we are going to frame learning this way. Minimize, this term is simply, instead of minimizing just the norm of W, I can minimize its square. It's the same thing. And the squared norm of W is just this term, W transpose W. Minimize W transpose W such that, and why minimize W transpose W? Because it gives us the max of 1 over norm W. Such that such that every point, not just the closest point, every point is at least, has a functional margin of at least 1. If every point is at least 1 unit away in that after projection, then the closest point will have a functional margin of 1. So y W transpose x is going to be greater than or equal to 1 for every point, which means it will be greater than or equal to 1 for the closest point, which means we can set the closest point to be equal to 1. If the closest point has y W transpose x equal to 1, then the numerator of that margin term becomes 1, and effectively by minimizing the norm of W, we are maximizing the margin. Yes?
So are we just imagining the closest point to be at a distance of 1 unit?
We are saying that we are going to, because we have this 1 degree of freedom in terms of the scale, we are going to scale the W so that, find a scaling factor so that the closest point is at a distance of 1. We are not imagining it to be 1, we are saying that there is this degree of freedom and I am going to exercise it.
What exactly do we mean by scaling the factor?
So what we will do is, so notice that this picture, I'm going to keep coming back to this picture because it's easier to draw it in 2 dimensions. So say this is the true weight vector. What I'm going to do is divide by some constant, or let's say I'm going to multiply by some constant. I'm going to try to find this weight vector instead of the original one. And hopefully I've convinced you that they are identical if C is a positive number. Right? I'm going to set C to be the following number. C equals 1 over or C is greater than or equal to, or in fact let me see. It's a constant, right? For a given training set, this is a constant. For a given training set and a given W. And it's positive. So I'm going to scale the W so that this quantity, by this quantity, and try to find that W. And I know that they are identical because positive scales don't matter. Which means now I have to search over these scaling factors. Or at least I have to constrain the fact that C, by definition of minimum, that means that C is greater than or equal to this quantity. Greater, sorry, I take that back, less than or equal. Which means this thing has to be equal to 1 over c, which I will set it to 1. As you pointed out, 1 is just an arbitrary choice. I could have chosen 17, and you will be carrying around the 17 everywhere. It does not change the optimization problem. It does not change the requirement of maximizing margins.
So whether you choose 1 or 17, it's basically what you're trying to do is just get the points that far away.
Exactly.
So why wouldn't it be better to choose something bigger then? Because like we talked about how a greater margin is better, right? So why wouldn't it be better?
Because when you actually get a larger thing, so consider in fact, here's a thought. So instead of thinking of the bias being outside, if your bias is inside, so then margin becomes, this disappears, right? So basically the margin is W transpose X divided by norm of W. If I had multiplied W by some constant C, that constant shows up here as well. So if I chose 1 or 17, it's going to get cancelled, the margin is going to be the same. Because you will simplify it. Because you are normalizing by the norm of W anyway. And 17 just means that you have to multiply by 17 everywhere during training. Questions? Other questions? Yes.
So the way I see it, where that scaling factor is just to make it easy to make the problem easily turned into an optimization problem. Exactly. So we want to make this, we care about maximizing margin, and we want to convert it into a kind of mathematical optimization problem that we know how to solve. It turns out this is actually a fairly easy problem to solve. At least if you have done optimization, this is a class of problems called quadratic programming. There are standard algorithms for this, and for the first maybe 10 or so years, the way to train an SVM was to use a technique from quadratic programming. Now we've thought a little bit more about this, and we have better algorithms, which are also basically optimization algorithms, but yeah. Other questions?
So do we get a different results if we use perceptron or?
That might be a homework question. You probably will. You probably will get a different result. The question is, what do you mean by different? You will almost likely get a different weight vector. But the question is really, are you talking about different in terms of the values of the weights or its predictions? Because if you really only care about the quality of the predictions, you really don't care about the value of the weight vector. And so you probably will get different weight vectors in terms of numerical values, but you may get very similar predictions, especially if you use something like an average perceptron. Maybe not necessarily for the vanilla perceptron, but average perceptron. Because this is probably a good time to mention this. The average perceptron, or the voted perceptron, which was actually the one that we saw just before average, is actually a technique for converting an online algorithm into a batch algorithm. So this idea of doing multiple epochs is really an online to batch conversion. You have an online algorithm, you go make it a batch algorithm, and voting gives you all the guarantees that PAC comes with. So once you go to average perceptron, probably the quality of the predictions will be the same. Maybe the weights not so much. So this is an optimization problem. We'll see how to solve the optimization problem later. This optimization problem is called the hard support vector machine, and it's hard not because it's difficult, but because it mandates that every positive point should lie on one side of the separator and every negative point should lie on the other side. In other words, this constraint here is a hard constraint. It cannot be violated. What's the problem with this? doesn't account for noise. And so what? Well, overfitting is less of a problem here. There's another, actually overfitting is not so much of a problem because you have this norm of W which explicitly controls overfitting. Because norm of W, maximum margin, minimize the norm, maximize the margin, which actually it turns out reduces overfitting. But there's another problem. Something related to what you said, but
Yeah, well, I think basically what he was saying is that it means that your data set has to be separable.
Exactly.
Pretty
exactly.
difficult.
This assumes your data set is separable. Let's see what happens when your data set is not separable. And we're not going to see it with proof by pictures, but we'll just think about it from the mathematical point of view. This is a constraint optimization problem. And the way to think about this kind of problem is minimize, or let me read out what's written there, minimize half W transpose W over all W's such that for every training example, Y W transpose X is greater than 1. Notice that the constraints basically define a set of acceptable W's, and your search in the top line is only over those valid or what are called feasible weight vectors. So each constraint there comes from one training example, and it says, simply says, that training example should be correctly classified. I can, that's all there is. And the collection of all of them define a set of feasible weight vectors that all of which are consistent. Going back to the earlier discussion, any weight vector that satisfies all the constraints will be consistent with the training set because it mandates that every point should be separable. And the condition on top, minimize the norm of W, simply says among all the weight vectors that are consistent, find the one that has maximum margin. If your data set is not separable, by definition, there is no weight vector that is consistent. So this constraints, the set of feasible weight vectors, is an empty set. So you are searching for the best element of an empty set. You'll get nothing. So there is no way of solving this problem if your data set is not separable, and your optimizer will probably complain. Make sense? Questions about hard SVM and why it's not everything? How would you solve this problem intuitively? I mean, don't think of math. What if there's one point, let's say there's this, your data set is perfectly separable. For all I, this condition holds. Except for this one I, which it just so happens is noise. Just one training example. How do you learn? What might you do if you have to
Throw it out.
throw it out? If you knew that some training example was noise, you could throw it out. And once you throw it out, all the remaining points will be separable. And that's really the intuition. What we are going to do is, if someone tells you, let's say you're given some training set, and if someone tells you that these two examples are actually noisy, you just get rid of them. And once you get rid of them, then use the rest of them to find the large margin separator. It's basically the same problem as hard SVM. So all we have to do is ignore data points that either make the margin smaller or the data inseparable. So the plus here, if the plus had not been thrown out, the margin would have been much smaller. The minus makes the data inseparable. So I'm going to throw both of them out. Yes?
Well, if I read this sentence here, then you can just jump to the idea that we'll pick the two farthest points away and then we maximize the margin over this, yeah? Where you know where to draw the line.
Yes. So really, if I paraphrase your question, the question you're asking is, yeah, I'm assuming, sure, if I assume that I have noise in these examples and I throw it out, life is good, but who's going to tell me which examples have noise, which examples to throw out? Because if I accidentally throw out the wrong points, I'm basically losing information. So that's the trade-off here. If I throw out all the wrong points, then I'm losing valuable information, and in the future I might just get, or I might end up with a weight vector that performs pretty badly. On the other hand, if I do not throw out the bad examples, then I might either end up with a very tiny margin, or even worse, an infeasible problem. So the game now is, how do I modify this optimization, the hard SVM optimization, to throw out as few points as necessary, and only those points. And this gives us something called the soft SVM. But before getting there is this point about throwing out examples, okay. Okay, so now we have to decide for a criterion. So now we want to do two things. Penalize, actually no, ignore some data points and say that they don't really contribute to this margin, and then compute the margin for the rest of it. And this seems like a chicken and egg problem, but there's a clean way of solving this in one shot. And the way to do that is to introduce something called a slack variable. This is the Greek letter psi. A slack variable is, think of it as a way of measuring whether this example should be thrown out or not. If the slack is 0, then it should not. If it is not 0, you're going to mandate that y w transpose x. Earlier, we required that y w transpose x should be greater than 1 for every example in the soft SVM here. Now we are going to say y w transpose x should be greater than 1 minus the slack. The slack gives some wiggle room for each example, and every example gets a different slack. So what this means is the slack variable for every example decides whether this training point should be ignored. In some sense, I like to imagine this as training points breaking into the margin. Should this training point enter the margin or not? And if the slack variable is 0, either the point is on the margin because y w transpose x is greater than 1, or it's on the correct side of the margin. If slacks are all 0, then the data set is linearly separable, right? Because it reduces back to the hard SVM, the equation, the expression on top. Questions about slack? What is missing? Yes?
How do you determine what is 1 now that you're no longer scaling based off of the point closest to the margin?
Right, you're still using 1, except you're computing margin using only those examples that have a slack of a non-zero slack, actually a 0 slack. And for those examples, the closest point will still be at, will still have the functional margin equal to 1. But there's a problem here. Sure, I introduced this new variable. Nothing tells me that, what stops me from throwing away the entire training set by setting slack equals, it's a positive number, so slack equals say 1 or minus 1 for every, 1 or 2 or 100 for every training example, effectively ignoring every training example. Would that be permissible? How do you avoid that?
Minimize the amount of slack.
Minimize the slack. We have this machine on top that knows how to minimize things. Might as well, we are anyway minimizing the margin, might as well in addition minimize the number of things that are thrown out or minimize the total slack. And that gives us this new optimization problem. I'm going to go over this in a bit of detail, but I just wanted to throw this out there to point out that the SVM is really these 3 lines. So what we do is we demand that every training point should have a functional margin of 1 minus the slack. Every slack variable should be positive, and we minimize the margin, which is we maximize the margin, in other words minimize the norm of W, and the sum of slacks. Really the only difference here is what we place the closest point at. So this gives us something called the soft SVM, and the way to interpret all these pieces are, as always, we are minimizing the norm of W, and minimizing the norm of W by the argument that we had at the beginning of this lecture maximizes the margin. That remains. There's this other term that we are minimizing, which is the total slack. In other words, what this means, allow as few examples as necessary to violate this margin condition. The constraints simply define what the margin is. It simply says what these slack variables are. It's exactly the same as what we did before, except there's this additional psi I in each constraint. Yes?
Is the slack a property of the examples?
It's another thing. Notice the other thing that changed between the top and the bottom is at the top the minimization was over W. Now it's part of the optimization.
But who assigns the slack?
The optimizer.
You said it was per example.
For example, so the slack is a giant vector of numbers, all positive, whose size is the size of the training set. So now we have 2 vectors. We have a weight vector W and the slack vector, and that I've just written it as psi. And now optimization has to search over every possible assignment to W and the slack. In some sense, what it does is this is not how it should ever be written, but you can think of it as, suppose the slack is, the entire set of assignments for slack is this vector, which implies that these examples are ignored. Now, write it down as a hard SVM using only the ones that have a 0 slack. Find the best weight vector. Keep that aside. Now pick another slack vector. Do the whole process again. Do this again and again till you find the smallest sum of these 2 things. So the smallest margin plus slack. Yes?
It seems like if you have one of the points that has a slack that's way, way out, almost to infinity, like it's going to drag the classifier over a little bit, and you may end up missing.
Yes, and in fact, that's a good point actually, because there's this other term here which I'm not had the chance to talk about. This C. C is a trade-off term. It lets you trade off between throwing away the entire training set and just maximizing the margin, which is basically setting W to 0 or minimizing W. If C equals infinity, so let's consider the case when C equals 0. When C equals 0, what we are saying is that it doesn't matter what the slacks are. Pick whatever value we want. I only care about maximizing the margin. This reduces to the hard SVM case. When C equals 0, we are focusing more on the generalization. The norm of the W basically improves generalization. When C is 0, we are saying we care more about generalization, not so much about this fact that some examples might not be linearly separable. When C is infinity, what we are saying is, I really don't care about generalization. But I demand that when C is infinity, the only way to minimize this quantity is to set the slacks to 0. When C is infinity, what we are saying is, I don't really care about generalization, but I demand that you should be able to separate this training set, which is overfitting. So C is this knob I was telling you about that controls overfitting and overgeneralization. I don't know if overgeneralization is the right word, but generalization. Questions?
I'm a little confused about what the plus means. Like, I thought the W and the epsilon has different dimensions.
No, but W transpose W is a number. It's the norm of the weight vector. The sum of the slacks.
But what you say is, you say the slack is a that long
Yeah,
vector.
that's just, I put this quantity here is simply, it doesn't matter, you can think of it as a vector, but it doesn't, you don't have to, it's just a collection of one. Yeah, this is not right very well. Basically, it's just, think of this quantity as a collection of all elements of this kind. You don't have to think of it as a vector, it's just a big bucket.
So, what is the significance of the slack being a vector?
It doesn't, it's,
Given that margin is not,
no, when I say vector, I mean, it's an array, if you want.
right?
It's just an array.
So why is there a specific value for every training example?
Because you are willing to entertain the possibility, think about it this way. You're willing to entertain the possibility that every training example may or may not break the linear separability, independent of all the others. That's the reason. So every training example gets this sort of effectively a slack, which may or may not be 0. If it is 0, then it gets no slack. But we don't get to decide, the optimization figures it out.
And we pick out the one that is the minimum of these?
We pick the one that has, if you look at the objective, if you stare at this objective, we pick the one that has the minimum sum of these two things. We find the W and the psi that minimizes the sum of the norm of the weight vector plus the total slack.
Can you go back to the slide where you have the 2 misclassified points in the graph? Yeah. Can you draw the slack on those two?
Yeah, sure. The slack on this one is this distance here. If this is 1, this is the slack on the positive example, the distance from 1. And the slack on the negative is actually very interesting. It's this distance.
Okay, that makes sense.
It's how far is it from the correct side? Both positive. Yeah, that's actually a good point. I'm probably going to make that. Anyway. Other questions? Yes.
I think you were mentioning if C is 0, that's like the arc SVM. And then what was the other side?
When C is infinity.
Yeah.
When C is infinity, the only way to satisfy that minimization, remember that, think about it this way. When C is infinity, here, my psi is still, I need to find a real valued assignment to W and psi. When C is infinity, the only real number that still leaves me with a real number here is psi equals 0. All the psi's. When psi equals 0, this disappears, this quantity disappears, and really this is irrelevant because see, when C is infinity, the only term that matters in the objective is the slack. So we are left with, when C is set to infinity, we are left with minimize W of 0 such that Y W transpose I greater than or equal to 1. So find a W such that every example is correctly classified. And this is interesting because basically what we're saying is we really don't care about generalization. Remember that this was the term that forced generalization. And by setting C to infinity, we are saying we don't care about generalization, but I demand that every training example should be correctly classified. So that's why it's overfitting. Questions, other questions?
So you said that was the one that's the same as the hard support vector machine?
It's actually worse than the hard support vector machine because it does not even have the regularizer. Oh, sorry, I have not introduced the word regularizer. It does not even have this term here. That's called the regularizer, but yeah, it does not have that term, which means we have no way of picking a weight vector or preferring one hypothesis over the other on the basis of margin, because we've thrown out that term. By setting C to infinity, we are saying this is irrelevant. So it's actually worse than the hard support vector machine. As an aside, here's an optimization problem. This here is a way of checking whether a data set is linearly separable. Minimize the function 0, the function that assigns 0 to every w. Find a w that minimizes w, but that minimizes 0, so it's always 0, such that this constraint is true. And this also, by the way, is a linear program. Those of you who have seen linear programs, this is a linear program. So let me just quickly mention one more thing in maybe the 3 minutes that are left, and we'll pick it up from this point in the next class. We can simplify this whole equation to make it way more interpretable than what it is right now. Notice we have two constraints that involve slacks. These two. The bottom constraint is simply saying psi I greater than or equal to 0. I can rewrite this one as psi I is greater than or equal to 1 minus yi w transpose xi. Right? They are the same. So I have two equations for each psi I, two inequalities, greater than 0, and it should be greater than this other term. But that's equivalent, I can merge these two into saying psi I is greater than or equal to the max of these two things. I can merge these two. Basically, if it is greater than both of these, it's greater than the bigger of those two. And thinking about it this way lets me write my objective in and then there's a little bit more math, but I'm going to probably pick it up in the next class. You can rewrite this whole constraint optimization problem and get rid of the slacks and replace the slack with this max term. Basically replace this with the max from here, and we get a single line objective that says find the w that minimizes the sum of the norm of weight vector plus a term that with as a summation over the entire training set. And in the minute that's left, I'm going to give you an intuition of what this means. So the first term is the same, maximize the margin. Minimizing norm of w says maximizing margin. The second term, the term inside the summation, max of 0, 1 minus y w transpose x, can be interpreted as a penalty. It's a penalty for misclassification for every example. If an example is classified, let's consider three cases. If an example is classified correctly, y w transpose x, in fact it's classified correctly, there's something more. It's classified correctly and y w transpose x is more than 1. Then 1 minus y w transpose x is less than 1 and this max is 0. So for an example, say for a particular weight vector, if that example is assigned a score y w transpose x that's more than 1, that puts it outside the margin, that example incurs no penalty. If an example is classified incorrectly, it has a penalty of 1 minus y w transpose x because it's on the wrong side of the margin and you want to penalize it by that much. The third term here is interesting. Third part, if an example is classified correctly and is inside the margin, it still pays a penalty. I see I'm a minute over time, so I'm going to pick up here in the next class and maybe spend a little bit of time because this is important and this gives you something called influx. So, reminder, there's a homework due today and I have office hours right now, so please, if you have questions, you're welcome.